Welcome to our presentation for a NeurIPS paper on NERF, Unconstrained Post-Prior Free Neural Radiance Fields. I'm Injae from Korea University. NERF or Neural Radiance Fields opened up a new chapter in novel view synthesis by demonstrating its capacity to generate high-quality novel view images, given only a set of 2D images. However, NERF requires accurate camera post-priors. Some follow-up studies have addressed this problem. For example, BERF and NOM-NERF successfully achieved joint learning of NERF and poses under relatively easy conditions. However, we observed that these studies failed to train with unconstrained image collections. It has three main challenges that need to be addressed. First, it involves more complex camera poses compared to other image datasets. Second, it has diverse appearance due to variation in weather and time. The third challenge is the presence of various transient objects in the images. So we propose UpNERF, which tackles these three challenges. First, we introduce candidate TAD for robust pose optimization. We observed that some images with distinctive camera poses fail to train. This image captures detailed part of the scene that make it challenging to find their pose. Ultimately, this leads to falling into local optima. To mitigate this problem, we made slight modifications to the architecture of NERF and volume rendering process. We introduced an additional MLP head called candidate head. It learns an image-dependent representations. By using the volume rendering equation below, we can prevent hard pose images from being forcibly fitted into the shared representation during the early stages of training. Here is the loss function being used. Our intuition is to consider easy pieces first to complete the large jigsaw puzzle and handle hard pieces later. Therefore, we regulate the influence of the candidate head through scheduling. By utilizing the candidate head, you can observe that the pose is properly optimized. The next challenge to be addressed is difference appearance between images. The given images do not ensure color consistency, so the RGB reconstruction loss which used in previous works is not suitable. To be less sensitive to appearance changes, we adopt the deep feature of Dino as a surrogate. We replace the RGB reconstruction loss with the feature reconstruction loss in the early stages of training. And there are two components related to handling transient occluders in UpNERF. As demonstrated in NOM-NERF, the monodepth prior provides robust geometric cues for the joint training of pose and nerve. However, its direct application is not feasible since transient objects must be excluded. We use transient confidence rate W, which is obtained by candidate density. It allows the exclusion of the transient part when applying the depth loss. Lastly, to ensure that the rendered transient objects do not influence the learnable pose parameters, we isolate the transient network pi from the NERF network theta. So the gradient of transient occluders do not flow into the pose parameters. By addressing these three challenges, UpNERF successfully trains unposed NERF with unconstrained images. This is a comparison of the training processes between BERF and UpNERF. So this is the end of the presentation, and please take a moment to explore our project page for details that were not covered in the presentation. You can also access our paper, code, and poster on the project page. Thank you for your attention.